Today, we're going to talk about solvent effects and how they might have an impact on substitution reactions and the Sn1 versus Sn2 mechanism. Solvents are really important when we're doing chemical reactions because they can have a dramatic impact on the success of that reaction. But in terms of, I always kind of leave this topic to the very end because in terms of deciding what mechanism is going to happen, looking at the solvent usually kind of clutters your mind and gives you one more thing to think about when really the decision can be made by thinking about the nucleophile strength or base strength and the type of carbon bearing the leaving group and so on. But really it's a very important part of the reaction because it's going to facilitate the reaction mechanism that's going to happen and or hinder the reaction mechanism, as we'll see. And so when you go into the lab and you're ready to do a reaction, the choice of the solvent that you're going to use is critical. And almost all reactions, I mean, there are some examples of solid state reactions where we mix two solids and a reaction happens. But other than that, really, what we usually do is we dissolve all of our reaction components into a solvent, and that way we can mix them together very easily, give them a chance to interact. They have a chance for collisions, opportunity to react with each other, but then also having it dissolved in a solvent means it's very easy to heat it, very easy to cool it, very easy to maybe distill off one of the products as it's formed and so on. So that is the standard, is to use a solvent. And so today we're going to look at different solvents that we can maybe choose from and see then how they're going to impact the reaction rates of Sn1 and Sn2 mechanisms. So I have on this page just a summary of leaving groups and nucleophiles and bases. This is also a nice summary of just, what's so cool about the Sn2 mechanism. That backside attack is fantastic. If we have a primary leaving group, so here's a leaving group that's on a primary carbon, which means the backside attack is very easy. There's no steric hindrance. And so by using all these different nucleophiles, we can get access to all these different functional groups. So it's a hugely important reaction for synthesis. We can make esters and alcohols and alkynes. All these different reactions rely on the Sn2. So that Sn2 mechanism we're going to see again and again and again throughout the whole year of organic chemistry. Okay, let's take a look at our solvents. Solvents are they're listed here in increasing ionizing power. So at the very, very top, we have the ones that are the most polar. This one, trifluoroacetic acid, is the most polar. And of all of these, all the way down at the bottom, diethyl ether is the least polar. Now you might notice that actually it's still polar. We still have polar functional groups. We have this the oxygen here. Remember, this has a bent geometry, so those two polar CO bonds don't cancel out. They're in an opposite direction. They're in opposite directions, left and right, but they both have this upward component. So there is a net dipole moment for something like diethyl ether. So all of the solvents that we're using here are polar. And that is critical because they're going to help stabilize charges. And when you think about the mechanisms we've seen, almost every single mechanism has charges, maybe in our starting material, maybe in our products, maybe we have carbocation intermediates. There's charges all over the place. So typically we use polar solvents, but we can have ones that are even the most polar, or all the ones that are up here. These are all described as protic solvents. And what makes it a protic solvent is that it has an OH group. When you have an OH group, that proton is actually acidic and exchangeable. That's a couple interesting features of that proton. And it's also extremely polar, very, very polar bond. It can hydrogen bond. Oops. Any protic solvent can form hydrogen bonds. And very, very good at that. Very good at hydrogen bonding, even just with itself. So we could see that every single one of these structures, has the OH. Of course, water has an OH. Alcohols, carboxylic acids. Here's another alcohol. Every single one of these has that OH group, and that's what makes them all protic. And those are all at the very top of our list as being very, very polar. Now, hopefully, if we compared a couple of these, like water versus methanol, do you see why water is more polar? Why water would be more polar? Because this methyl group here, right, is nonpolar. So when you add a nonpolar region, because carbon-hydrogen bonds are not polar, that makes it less polar than water, which has just polar OH bonds. And what do you think about ethanol versus methanol? What do you think about ethanol versus methanol? Does it make sense to you why ethanol is less polar than methanol? Methanol is more polar than ethanol. Yeah, this has a larger nonpolar region. The ethanol has a larger nonpolar region, so it's going to be overall less polar. Okay, so these are varying in degrees of polarity. The CF3 group, right? This is very, very electronegative, pulling electron density towards those fluorines, so that makes this even more polar than an ordinary carboxylic acid like this. So trifluoroacetic acid hopefully would make sense to you that that's more polar than acetic acid. Okay, so so just a little comparison here of some, and recognizing that these are all examples of what we describe as protic solvents. So if we had something like water, methanol, ethanol, sometimes, you know, acetic acid, those we would recognize as extremely polar, and also we would call them protic solvents. Okay, all the other solvents here are very commonly used in organic chemistry, organic reactions. They're all aprotic, and so a lot of times we describe these as polar aprotic because that fully describes them, because they have no OH and they have no but they're still polar. They have no OH, but they're still polar. And so what solvents might we encounter? Things like acetonitrile. DMSO stands for dimethyl sulfoxide. A lot of times we use these abbreviations. DMF stands for dimethyl formamide. Acetone, that's probably the solvent you're most familiar with in using in lab to clean glassware, and also, you know, nail polish remover. Some are acetone based. Chloroform is CHCl3, and then both of these are examples of ethers. So, right, we have a carbon-oxygen-carbon bond. That's what we have an ether. This is called diethyl ether. So if you just use the word ether in the lab, the instructions are referring to diethyl ether. And this one is called THF. That stands for tetrahydrofuran. Okay, so these names, ether, THF, DMF, DMSO, if you ever see those names, you should just recognize them as something that's a solvent. That's just an ordinary solvent, and it fits in this aprotic category if you care about that, and that's going to help you discuss the reaction. These are all aprotic solvents that are commonly used, and so you can, other than recognizing that it's a solvent, don't worry, it's not going to be involved in your reaction in terms of the product that you're drawing, right? It's a bystander. It's observing what's going on. It's helping the reaction happen, but we're not going to include it. We're not going to incorporate it at all into our product. The exception, of course, is when we have things like ethanol, methanol, water. We've seen examples where those both act as the solvent, and those are the nucleophile in the reaction. Remember when we had solvolysis reactions, those were the reactive species. Okay, so what impact might these have on reactions? Let's take a look at Sn1 and Sn2 reactions and see how those are impacted by your solvent choice. Okay, so once again, we need a polar solvent of some kind. Why? Because they are going to stabilize the charges. That's the key here. That's what a solvent is doing, is it stabilizes charges. So the protic ones, we said, has an OH group, which makes them acidic. So that's going to be an important factor down the road. Actually, we're going to come back and visit protic and aprotic solvents, and we're going to want to avoid the acidic proton in some reactions. Okay, they're extremely polar. They can hydrogen bond much more effectively. And they strongly stabilize charges, They really surround those charges. We call that solvation. We call that solvation. Okay, and actually, you know, a lot of times we do calculations, we do modeling, we try and like see what these reactive species look like these molecular interactions. And so I have one of those to explain the solvation on how solvent molecules really surround an ion when we see it, and it looks something like this. Okay, so not a chemical illustration of any kind, but this I think is such a great illustration. If this poor cat is representing some kind of ion, maybe a cat ion, we don't have to go there, but it's an ion, so it could be positively charged or negatively charged. But what's going to happen when you put that in a solvent? So these little styrofoam balls represent a solvent. It just hugs that. It hugs that ion. Solvents, Protic solvents especially, love ions, and they're going to surround it just like the styrofoam is with that cat. Okay, so that's the image I want coming to your mind when you picture a Protic solvent surrounding a cation or an anion. All right, so let's see what happens with our mechanisms when we vary our solvent. So let's think about increasing the solvent polarity. If you increase the solvent polarity, then the Sn1 mechanism is going to be faster, but the Sn2 mechanism is going to be slower. So there's the big key. By increasing the solvent polarity, that's a good thing for the Sn1, but that's a bad thing for the Sn2. Okay, so for example, what does it mean to increase the solvent polarity? If I used a Protic solvent instead of an aprotic solvent, right? Because Protic is more polar. Or if I maybe had a mixture of ethanol and water, if I had an 80% ethanol and then I moved it down to a 50% ethanol, if I increase the amount of water, right? If I increase the amount of water, that's going to increase the polarity, because remember, water is more polar than any alcohol solvent. Okay, so those are some ways that we can maybe increase the polarity. Okay, so here's the question: why is a more polar solvent good for an Sn1? Why is that something that would speed up the reaction? Okay, here's an example of an Sn1. I have tert-butyl chloride and water. Remember, unimolecular reactions like Sn1 go through a carbocation intermediate, and then water is going to attack, right? Water is going to attack as a nucleophile, and after we deprotonate, we get to our final product. Okay, so of this whole reaction, what is the least stable species in the whole reaction? It's clearly this carbocation intermediate. It's positively charged, it's missing an octet. So this is the most unstable reactive species in the whole reaction path. Okay, so what happens when I use a more polar solvent? That more that carbocation will now be better stabilized when I use a more polar solvent. Let me highlight that so I could see it a little better. Maybe it will now be better stabilized. Remember why? Because like the styrofoam hugging the cat, it's going to be hugging that carbocation, and solvation is something that brings down the energy. Okay, and so that means that if the intermediate is more stable, lower energy, that means the transition state is also more stable, lower energy. So if we compare a polar aprotic reaction path that we're showing here for our Sn1 mechanism, when we put in a protic solvent, our carbocation is going to be better stabilized, better solvated, right? This is our solvated carbocation, and so the path for the substitution is going to be this one. So the blue path is now what it would look like if I used a protic solvent instead. A protic solvent brings down the energy of that carbocation, which makes it what? A faster reaction. Do you see that? This has a lower energy of activation. This will have a lower EA, so it's a faster reaction. If you decrease the height of the hill, If you have a lower energy of activation, you increase the rate of the reaction. So, carbocations are so unstable that they really need to be hugged by that solvent. And it turns out that actually Protic solvents, a Protic solvent is required for carbocation formation. You have to have a Protic solvent if you want to make a carbocation. Now, in all the examples that I've worked on that were either E1 or Sn1 that involved a carbocation, luckily we always had a Protic solvent because that is so common. Very often we're doing solvolysis. Okay, so the take-home message, the take-home conclusion here is that Sn1 is faster in a more polar solvent. And again, by what does that usually mean? That usually means a Protic solvent, such as water or an alcohol, because those are the most polar solvents we have. All right, so high polarity, good thing for a carbocation, therefore good thing for an Sn1. Now, what happens with an Sn2? We said for an Sn2, uh-oh, bad news, bad news. Suddenly it was not as reactive. Okay, so let's take a look at an example of an Sn2. Sn2, we have hydroxide, strong nucleophile attacking. Remember, this is just our one-step mechanism. Attacks the carbon, backside attack, kicks out the leaving group. Attacks the carbon, kicks out the leaving group. And so what does that do? What does that give us after that one step? We get the substitution product. Our leaving group is gone, and we have our substitution product. Now, when we look at this whole reaction process, everything involved in the mechanism, who is the most reactive? What is the least stable species in this whole mix? Okay, in this case, it's the nucleophile. This is our nucleophile. This is our leaving group. Remember, the definition of a leaving group is that it's a stable anion. So by definition, the nucleophile is going to be something that's less stable. So this is the most unstable reactive species. The Sn2 requires a strong nucleophile to attack. Okay, so what's going to happen when we put it in a more polar solvent? It will now be better stabilized. It'll be better stabilized by a more polar solvent. It's going to be hugged by that polar solvent. And so if it's more stable, that makes it less reactive. That's not what we want for an Sn2. We want a highly reactive nucleophile. So what does that look like in our energy diagram? What we could look at here is this is our nucleophile. If we put it in a more polar solvent, our nucleophile is going to be better stabilized, lower energy. So for it to do this same Sn2, this is now going to, it's going to end up at the same place, right? But what's going to happen here is now we're starting from a lower energy, so we have a higher hill to climb. This now has a higher energy of activation. And what we're looking at here with the blue path is the Protic solvent. So because of the Protic solvent, I'm going to end up increasing my energy of activation and therefore decreasing my reaction. So therefore the Sn2 is slower when I use a more polar solvent. So how can we make, what's ideal for an Sn2? How do we make the Sn2 as good as possible? By a solvent that doesn't hug onto that nucleophile, kind of keeps its distance, doesn't get attracted to it as much, a less polar solvent. In other words, what we're going to use is a polar aprotic solvent. The key here is that a polar aprotic solvent is polar aprotic is ideal Sn2 solid. So when you really want to do an Sn2, we're going to use what kind of solvents? What do we have? What do we have as polar aprotic solvents? This is what we're going to see again and again for our SN2s: acetonitrile, DMSO, DMF, acetone, THF. All of these are going to show up. So again, kind of get used to seeing those. That doesn't guarantee it's going to be an SN2. It just means it's ideal for SN2 conditions. You still can't have any steric hindrance. You still need a super strong nucleophile, but assuming those are in place, when I go to the lab and do this reaction, I'm going to choose an aprotic solvent to do the reaction, because a protic solvent is just going to hug on that that nucleophile and make it less reactive. The aprotic solvent kind of keeps that nucleophile more exposed, more naked, and ready to react. So that is ideal. Okay, so just a brief introduction into solvent effects. Hopefully that will help answer some questions down the road. Thanks for listening.